So in this video, we're going to talk about something called differentiability, and we have this explanation right here. And basically, what differentiability means is that the derivative exists at a particular point. Okay, so this really implies two things. The big one, first of all, is that the function is continuous at that point. We'll explain that in a little bit, and that the derivative to the left and right of the x value are equal. So remember that the derivative itself is a limit. And remember the first thing we found about limits is that for a limit to exist, it has to be the same at the left and the right of a point. So therefore, if the derivative is a limit and the derivative is different to the left and the right of a certain point, that means the derivative at that point cannot exist. Okay? So let's talk first of all about conditions where functions are not differentiable. So the first would be discontinuities. Okay, what types of discontinuities are there? Well, we have infinite discontinuities, like vertical asymptotes. So again, with what I just said about the limit, realize that our slope or our derivative, let's say this point is x equals a, our derivative to the left of that point would be a very big positive number. Our derivative to the right of that point would be a very big negative number. So therefore, the derivative is not the same on both sides of that point. So therefore, that infinite discontinuity would represent a point where our function is also not differentiable. Now, when we have jump discontinuities, something like this, the reason why the derivative doesn't exist right there is because, remember, the derivative is a slope of the line tangent to the curve, okay? There isn't really a line tangent to the curve along that point. Also, realize that in a jump discontinuity, we've basically provided a change in the function without any change in the x value. This is essentially like saying we have a rise over run where we have no run. So this basically logically just doesn't make sense. So we can't have a slope of the line at a jump discontinuity. And finally, at removable discontinuities, these don't work either, because if the function isn't defined here, I don't know what the slope of the line tangent to that curve is at this particular point. Now that might sound a little bit confusing, because yes, the derivative to the left and the right of that point would be the same. However, because the function is not defined at that point, there cannot be a slope of the line at a point where the function is not defined. It just doesn't work that way. So anytime you see a discontinuity, you immediately know a function is not differentiable. So that's kind of like a situation where if a function is not continuous, it means that it's not differentiable. But if a function is not differentiable, that doesn't automatically imply that the function is not continuous. And there's a couple examples of that. The first one is corners. So a corner is when we have a function like an absolute value function, let's say, that has a sharp corner right there, okay? Again, when you look to the left and the right of this x value right here, we would get, if we call this x value a, we would get a positive derivative to the left of that and a negative derivative to the right of that. So again, the derivatives don't match up on either side of the point. That's not differentiable, okay? A cusp is very similar to a corner. A cusp looks something like this. So it's not quite a corner. It's basically a corner where the slope on one side, let's say that's our point A, the slope to the left of A would approach positive infinity. It would be going very high up. And the slope to the right of A would be going to negative infinity. So again, the slopes on either side don't match up. The derivative does not exist. It's not differentiable. Now finally, vertical tangents, those are in functions that look something like this. So right at this point right here, if we drew a line tangent to that curve, it would look like a vertical line. And an infinite slope, the reason why that's not differentiable, or why we don't know what the derivative is right there, is because an infinite slope can't really exist at a certain point. That means that if you took any run, the function would just shoot up to infinity, okay? But that's not what happens in this case, all right? So those are the four conditions in which a function is not differentiable. So let's look really quick to a Desmos file which kind of illustrates these. So first of all, we'll see these two functions plotted right here. Now, if I asked you what would this function be, if you combine these two functions, we could have a piecewise function that f of x would be equal to 2x plus 4 when x is less than 0, and 2x plus 5 when x is greater than or equal to 0. So therefore, we would have a closed circle right here, an open circle right here. Again, if I asked you what the derivative on either side was, well, the derivative on the left side would be equal to what? It would be equal to 2, because that is the slope, I'm sorry, not that one. That is the slope of this line right here. Now, this derivative right here, anywhere around here, would also be equal to 2, because that is the slope of this, of this line right there. So even though the slopes match up on either side, remember that there's basically no way we could make this jump from this point right here to this point right here without essentially having an infinite slope. An infinite slope is another example of a vertical tangent. So in this case, the function is not differentiable at the point x is equal to 0. So if we instead look at another example, let's add this one and take that out. So now we have a function that's continuous, okay? However, what we have right here is a corner at that particular point. So if we looked at this function, again, this function is given, if we want to rewrite it, we would have f of x is equal to 2x plus 4 when x is less than 0, and 4 when x is greater than or equal to 0. So if we look at the function right here, we would have that f prime of 0 if we go to it from the left, so let's call it 0 minus. That's going to be equal again to 2, because that's the slope of this line. But if we look at the derivative f prime of 0 plus, that would be equal to 0 because we have a horizontal line. So again, in a corner, we have a mismatch of the derivatives on either side of the point. So therefore, that function is not differentiable at that particular corner. All right? So let's look at another example that's a little bit closer to this, but now we're going to switch things up. And what if we have a function like this? Okay? Well, if we have this particular function, we can write this function as x, it is, what is that, x squared plus 4 for x is less than 0, and 4 for x is greater than or equal to 0. So our function is continuous at this particular point, and if we look at the derivative here, we would have that f prime of 0 minus would be equal to what? Well, if the function is x squared plus 4, that implies that the derivative would be, we know the power rule now, 2x, okay? So f prime of 0 would be 2 times 0 minus, which is basically just 0, okay? When we looked at this function, we already found out that f prime of 0 plus from the last example was 0. So in this case, the two derivatives match up. So even though this is a piecewise function, this function would be differentiable. So we get a big smiley face right there because the slopes or the derivatives to the left and the right of this point where the two functions join at x equals 0 would be the same. Okay? So whenever you get piecewise functions and you're looking for differentiability, do an analysis like what we did right here. Look at the derivative at the left or the right of those connecting points in the piecewise function. That'll tell you whether or not the function is differentiable. All right? So now let's look at the examples of the other types of functions which have places where they are not differentiable. So the first example, this is like a cusp, okay? So again, if we zoom in on that cusp point, what we will see is that if we compare the derivatives or the slope of the line to the left and the right of that point, we'll see that to the left of that point, well, our tangent line is going really steep negative. It's actually going to negative infinity, whereas to the right, it's going really steep positive. It's actually going to positive infinity. So if we have, in this case, f prime of 0 minus is negative infinity, f prime of 0 plus is positive infinity, well, that gives us a bit of a problem because, again, the derivatives do not match up on either side of that particular point, so therefore a cusp is not differentiable. Okay? And finally, as our last example, let's look at the vertical tangent right here, x to the 1/3. So if we look at this point, again, we have a vertical tangent point right here. So you might be saying, well, hey, from the left and the right, it looks like this derivative is approaching infinity. But again, we can't have a derivative be infinity because if a derivative, we write it as dy dx, that's basically tiny rise, right, tiny, over tiny run. Even though this run is a tiny number, it cannot be 0. And basically, if dy dx equals positive infinity, that implies that our run is equal to 0. We can't have that, okay? So a vertical tangent doesn't work. We can never have a tangent line be infinity because, again, think about what that implies. If a slope of a line tangent to a curve is infinity, when you are looking at, let's say, the graph of a derivative, if we were going to graph a derivative, let me erase this right here. If we were going to graph the derivative at this point, the derivative, we'll say this line is f prime of x, it would look something along the lines of this. Okay? It's approaching positive infinity at both points. However, the problem with this is differentiable is kind of another way of saying our derivative function is continuous. And in this case, we have a big old discontinuity right there in the function for our derivative. So therefore, this is not differentiable. So there you go. That's a quick summary of the 4 types of situations in which a function is not differentiable. So come tomorrow with class with questions if any of this is still confusing.